Okay, so good morning, and we're getting close to the end of the course. So let me get back to something I was doing last class, do a quick review of what we did so I can present to you a little bit of asymptotics of integrals, just a little bit. Remember I mentioned that in this course we saw asymptotics of differential operators, which is doing the reduced modeling, getting some complicated PDE and getting some less complicated PDE, which usually are useful to do some theory when possible and also to do computations. We saw a little bit of asymptotics of solutions, right? And like average and so on. And now we'll see a little bit, we got to a situation where we're going to see we need asymptotics of integrals. All this, just a little bit, there's like sometimes just books, a full book on asymptotics courses, which is very important. So where are we? So we were looking at the Burger's equation. Let me remind you of what we saw, right? The viscous Burger's equation, or originally called the Burger's equation. Okay. Then we use the Kohl-Hopf transformation, which was this change of variables, the x, okay, that told us that V satisfied a heat equation. Okay, this is what we saw. So to a very nice step, which means we have this more complicated equation here. We saw how to solve this using the Gaussian kernel, the fundamental solution of the heat equation. And with this change of variables, right, we sort of linearize the problem, and then we go back and forth and so on, okay? This reminds, as I mentioned to you, a little bit, change of variables reminds a little bit of change of variables you see in ODs, which is for the Riccati equation, which is a nonlinear ODE, which you can do a change of variables and it linearizes things. Remember also that this equation here, we were able to, I showed you a solution that was something like this. Hyperbolic tangent for two constant states, right? And we saw that this part here scaled with epsilon, right? There was the hyperbolic tangent, and that you ask for a traveling solution of this guy. I didn't do all the details, but I gave you the solution. Sometimes I give it as an exercise. You rewrite this as an ODE. You integrate, you impose conditions at infinity, but out comes that hyperbolic tangent, which has this, which is sometimes called the viscous shock, right? Because this scales, okay, scales with epsilon. So there was a hyperbolic tangent. As epsilon goes to 0, this guy becomes steeper and steeper, right? So this is an easy way, say, to see how viscosity smooths out, regularizes the solution, and even more complicated, how you sort of recover the shock coming from above, that is, letting epsilon go back to 0 plus. But this is not so difficult to do when you have these constant states. With this Burger's equation, in the solution we did last time, we were doing this for a generic Burger's with conditions and so on. And now let me write, so maybe that improves the discussion. And we found this ugly-looking solution, but which is a solution, right? It's exact. So we found this. So through the Kohl-Hopf transformation, we go solve the problem in V, come back, we have to adjust with the initial condition, and we found this. Or did I write the G? Oh, here it is. Where we had that. Right, because we had to change from the initial conditions to here to the initial conditions in here, which had to solve an ODE, which had this kind of integration factor, right? Telling the story in just a few words. Okay, so this is our, as I mentioned, our not so nice, not so friendly looking solution. Okay, so this came out of solving. See, you see something that looks like a Gaussian here, right? Solving the heat equation, going back and forth. And then we say, oh, wait a minute. Oh, no, it's okay. Let me see. Yeah, it's okay. So then using this, okay, skip them, but that's good. So we can write this like this, trying to make it look a little nicer. So it is useful. I think I presented it okay. I didn't skip anything. Sometimes when we do a review, let's write this in a slightly better looking for exactly the discussion. This is good for the discussion I want to do now. Okay, yeah. Sorry, I got a little confused here, so sorry that I hesitated a little bit. So basically because I'm just giving the highlights, then, right, I don't remember all the steps, that's why I hesitated. So here's using G, this little G that formed and so on, you plug it in and you can rewrite the solution in this way. Okay? And this way, with this big G given like this, now we have it kind of ready to do the asymptotics of integrals when a parameter, say, goes to 0 or a parameter goes to infinity. Here actually, quote unquote, there's a parameter going to infinity because the parameter is 1 over epsilon. Okay? So let's leave this as here. Okay? So we want to study this. So basically, we want to study this. Study in the limit of vanishing viscosity, which is epsilon goes to 0. Or in other words, 1 over epsilon going to infinity. So we want to see, another way of saying this is the limiting, I won't write everything. So the limit of vanishing viscosity is the limiting, how the regularization, as the regularization disappears from above. Okay, so from a PDE's point of view. And basically we want to see the behavior of the regularized. So this is more in a PDE language, right? When I talk about viscosity, it's more in an application terminology. Now, in a PDE's terminologies, we want to see the behavior of the regularized solution as epsilon goes to 0. prior to a shock, right? So this is before a shock happens, right? So this guy, right, going like this before the shock time. And as I already mentioned, for this guy here, as epsilon goes to 0, this converges in a strong way. I don't need to integrate anything, right? For the KdV, as the dispersion parameter goes to 0, because there's a lot of oscillations, then it's a weak convergence. We have to see it in a sort of an integral form, okay? So we saw this clearly here, and we're going to see this now clearly with this sort of not so good-looking object. That's what we're about to learn, okay? So we will see in a few steps, because I'm not going to do all the details, that basically as epsilon goes to 0, this guy, not friendly looking, not pretty looking, gives us back the solution we would have with characteristics. Okay? So note that here, epsilon goes to 0. It's a little bit of a singular limit because a higher derivative is disappearing. And actually, right, the PDE is changing type. Okay, so super quick, I even write this, super quick aspect of, let me put it like this, integral asymptotics. Okay, there's many books on this, right? One book I like, because I like complex variables and so on, it's written by two great researchers in waves. So one book I like, and I will be using it, it's a book by Ablovitz, Mark Ablovitz, and Thanasis Fokas, which is complex variables. And go to page 400 and something. So this is like page 422. Wait more at the end, there's like the parts on asymptotics. So let's go a quick view on Laplace's method. And then I'll talk on stationary phase, right? But there's like, this book is a good book, is a thick book on complex variables, but there's like books just on asymptotics, okay? And asymptotics of integrals and so on. All right, so take this integral here. I'm going to call it integral that depends on the parameter m. Okay, the presentation I told you is going to be superficial and fast, but just to give you an idea. And suppose you have this integral, phi of t, phi prime, no, f of t, sorry. They are smooth. In AB, there's a point where this guy is 0. This guy here, which in the next case, which is stationary phase, we will have an I here, right? This is a decay rate. In the other case, it's going to be an oscillatory object. So sometimes I get almost tripped on my tongue and I say that this is a phase. This is not a phase here, because this is not an oscillatory term. It's a rate of decay. So basically, if the rate of decay to some extent is stationary, boom, it has a point where it sort of slows down. That's the point where sort of you pick up, you feel something interesting. The same thing will happen with an oscillatory one, okay? So, and this guy is greater or equal to 0, okay? For some point in the interval, so let's get a little bit of an intuition for what happens, right? It's like, I mean, some things on integrals like this, you can do it rigorously and so on. I'm going to do it formally so we get just a flavor, okay? So some intuition. Okay? So let's see the following. Some intuition, let me say, for the main contribution, so the dominant, right, for the main contribution which comes from the neighborhood of C. Okay, so you see the decay rate here of this guy somehow is depending on time, and at some moment it's not varying, right? So let's see the contribution for that. So let's call A just to give a name for the integral over this small neighborhood of the point C, okay? And if I use Taylor series, okay, for F in a very cheap way, for the other part, I look at one more term. Okay? Can you see what I did? Basically, take this integral. Because I'm doing a very sort of crude thing, just get intuition, I'm not even going to put approximations or higher order terms. I'm just going to call it a new name A so nobody cares, right? So I'm taking a little slice here near C. The approximation of F is the cheapest one I can do, just F of C. The approximation of this term, I take the first two terms of the Taylor series. I don't have the first derivative because by hypothesis, this guy is 0. That's all, okay? So we want to have an idea how this guy looks like, okay? So just to get into it. So I'm going to just throw you things without, doing this intermediate steps. This is in the book and so on, and in text. So let me put it here. Let tau, this auxiliary variable here, new variable, let's call it this guy, just to try to simplify the way the integral looks like. So if I get this variable here, do I have it right? Yes. I can then write A in a form that's going to start looking like this guy. So it will be useful, right? Or that guy will look like this guy, right? That's maybe the proper way to say this. So the steps I'm skipping are basically algebra. Okay, we're at tau 1. I thought I had written this wrong. So I don't want to go over all the calculations. So this guy. Okay. So this is rewriting this term on the window. Okay. We will use the fact that this is square root of pi. So this is smaller than that. I mean, it's just a little portion of that, right? And therefore, so in the regime, so what can be shown is that in the regime where m is much greater than 1, again, I'm skipping algebra and details just to give you a flavor. Okay, we have, let me put it over here, that why did I write I? I think I have a typo. Why did I write I of k? Well, let me put this. I is asymptotically So basically, right, I mean, if you look at this integral, you say, well, when m goes to infinity, this is going to decay, right? This whole guy is going to decay, but you're integrating, so on. How is this guy sort of decaying also together? Basically, this is a slightly better way of seeing it, how it's decaying, right? The rate is going to be at this point and so on, how it's sort of slowed down, the decay, and it looks like this. And this formula, okay, this sort of approximation will be used. I'm going to just talk about the stationary phase, but then I'll come back to this approximation and use it for these ugly guys because they kind of look the same, okay? So basically, as you will see, since we sort of motivated, this is very sketchy, very, very sketchy. Since we motivated that things, the main contribution comes where this guy is 0, right? We are going to differentiate this guy here in y, see where it's 0, and do that approximation near 0. Okay, that's the story in a nutshell. That means very, very brief storytelling, and here just the sketchy thing to motivate, right? Give the intuition. Another type, just so I mentioned about integrals of asymptotes of integrals. Now let's take a Fourier type integral that looks like this. Okay, so now the difference is that this guy here will oscillate, right? Later on, not yet, but later on, I'm going to put a phase here. This is just to remind us. What I'm going to do now is just remind us a little bit of the Riemann-Lebesgue lemma. Do you remember? Have you seen the Riemann-Lebesgue lemma and sort of what it says? No? I mean, again, no problem, so there's more for me to tell. But the Riemann-Lebesgue lemma is like an integral, say, of f of t together with the cosine of mt. Remember, and when m goes to infinity, or n goes to infinity, you get that the integral is 0, right? And that for us, now with what we've seen in this course, and I'll do a drawing in just a second, is kind of intuitive. Because the cosine, it's a little bit like the weak convergence of things when you have oscillation, the KdV and so on. Things start oscillating so fast, so fast, so fast, so fast that there's cancellation. Okay? And what I'm about to talk in a second is basically stationary phase, because the Riemann-Lebesgue lemma looks a bit like this. When k goes to infinity, this guy dies, right? But if this phase here is a function, it's more complicated. Then if the phase has a stationary point, which means derivative equal to 0, there's a point where it slows down a little bit, and that's just enough to pick up something non-trivial. Okay, that's in words. Let me show you the highlights. Okay, all right. So here, take this guy, f of t, smooth in AB. Okay? Okay. So let's just for a second. Let f of t be identically equal to 1. Just for a second. So therefore, the integral from a to b dt, okay, is going to be equal to minus a over k something like this, okay, and which goes to 0 as k goes to infinity, right? The case like this. And and if you see then the Riemann-Lebesgue lemma, you can keep on integrating things here by parts, generating terms and so on. I mean, if you look at in all detail, you can see the proof, but then along the lines, then say the Riemann, let me just write it here. So the Riemann Lebesgue lemma says that the limit as k goes to infinity of a over b f of t e to the I kt dt is 0, right? If this guy here, having, say, this guy here bounded, okay? And the intuition, as I mentioned to you, is this, right? So if I have, say, the function, if this is a little piece of the function f of t, and right? So this is my intuition, the intuition of Riemann-Lebesgue, right? So as this guy starts speeding up, this locally, it's almost like this guy is a constant. So there's cancellation, right? It's not so simple, but then that's why this integral is like this. But now, if we have Fourier type integrals like this, which is really more of interest, right? Which appears in the things we saw, now, this is the guy we're interested in. And these are type of integrals we saw somehow in our wave problems, right? Where this is the phase, right? So it's more complicated than the one above, more complicated than the Riemann-Lebesgue lemma. So what can be shown, so the stationary phase, so this implies there's a method called the stationary phase method that tells us that the main contribution to the integral comes from the neighborhood, or comes when, instead of from, comes when d phi dt is equal to 0, right? This is what means the word stationary phase. Right? That's where sort of the phase slows down, and that's where the main contribution comes in. I'm not going to give details, but you can sort of also formally do Taylor series expansions and see how the contributions come. Of course, if you want to prove things, you've got to be more careful, but stationary phase is a method that appears many situations where I have an oscillatory Fourier type integral. I'm really telling you very I'm not even giving you a short course on this. It's a little bit like a commercial on TV, right? Look, go and buy this because it's really good for you. So this is a little bit, it's a commercial. What I'm doing here is a commercial propaganda on asymptotics of integrals, right? It's not supposed for you to learn, but it's good. It's the end of the course. You hear about this. And that part, I'm sure, is that you can see is that we're about to use this for the Burgers problem, and these type of integrals, you've seen it here, particularly in dispersive problems where we cannot really write the solution in closed form and this and that, and we have integrals, and then you say, oh, how does this water wave solution look like? And there are situations where you do stationary phase type approximation. So you see stationary phase in waves books, like Witham's book that I mentioned, right? And Stoker's book, which is just on water waves. So you see this type of already old but very useful techniques for asymptotics of integrals. And here's just, as I mentioned, a commercial, propaganda, right? It's not really, not even a short lecture because I'm not doing almost anything. Okay, so now let's go back to Kohl-Hopf. Kohl-Hopf plus Burgers, or it should be said Burgers plus Kohl-Hopf, doesn't matter, right? So doesn't alter the sum here, doesn't matter. Okay, so therefore we need to satisfy the stationary point well, we have, as I mentioned to you, we have to compute the G, D, G, dy. Going to be f of y minus x minus y over t, okay, equal to 0. Okay, so let me go back here. See, now, here, what we learned in a very sketchy way is that this guy here, this is where the contribution comes from, right, without much deal. Well, now who's that guy? It's basically this guy here and here, but they're the same. So we can check for one and for the other. What really changes from here to here is this guy, but we'll pay attention on it later on, okay? So if I solve this, right, to find my stationary point, look, the integral is in y. So let me just highlight this like this. I have to solve y. I'll solve y in terms of x and t. So this will give me y, a function of x and t, right? This is, let me call this quote unquote the stationary y. I'll just use this notation. It's actually the xi. Right? Or maybe it's even better to write like this. The xi is the stationary y. The guy that solves this. Okay? All right? So then, right? Which, in other words, if I want to, in the notes, what I did, let me do it what I did in the notes. It becomes like this. Okay? This is my notation. It's the guy who solves the stationary y. Okay, now, 1 over epsilon going to infinity, right, which means viscosity going to 0, plays the role of our m, and then using results above, we have that, the integral minus infinity to infinity of g of y is asymptotically g of xi right, g of epsilon. Okay? And if we apply this, so we can use this, in the numerator and denominator of u. Okay, which gives this. Let me see how I write this without skipping too much Well, let me just repeat. I think it's best if I repeat this. Look. No, I think I have something wrong in the notes. No. Oh, the G is already inside. Okay. No, what am I doing? Oh, I see what I'm doing. Sorry. Sorry, my notation is bad. I think, let me put, because the G, see the G is that G over there, but here what I'm doing, sorry, have to fix it. Let me put in a tilde here. Let me fix this, I think, I didn't notice this notation, bad notation. Because it's basically this, look. Here is one, and here's this guy, right? But G here is not the same G here, because now I'm writing with a capital G and so on, right? So that's why the notation is bad. And let me write this, where G tilde is equal to x minus y over t for the numerator, and G tilde is equal to 1 for the denominator. Please ask questions because I messed up with the notation and then I might have confused you, okay? I got to fix maybe in this notes, I don't know why. I used the little g here, right? Which I also used it over there as the sort of initial condition and so on. So basically, what I want to do here, what I want to do here is I want to use this asymptotic formula here that we got from Laplace's method for the numerator and the denominator, okay? The denominator. In the numerator, this guy is this. In the denominator, it's 1. So in the numerator, so basically, I have to now, for the asymptotics of the solution for u, right? What I'm going to do, well, let me put it for the interesting. So for u, what am I going to do for u? I'm going to do this formula here, where this guy in the numerator, and this formula here, with this guy in the denominator, okay? But now, the fact that these guys look alike, this junk here cancels because it's in the numerator and in the denominator. So what will survive is I'm going to get 1 here, and I'm going to get this G tilde, but it's not, I'm not going to write it like that. How am I going to write it? It's G tilde evaluated at Xi. Oi? Aqui. Esse aqui, exatamente. Exactly. So we get this. X. Right? Over T. So now it's not 1. Okay? And then, so this is my solution, u of xt. But as you were pointing correctly upstairs, right, Lucas, who is this guy? Is f of xi. Okay? And therefore, we have basically a solution, right, f of xi, where xi is our stationary point, and we have a solution that looks like the initial condition traveling. Well, not, kind of. I have to be careful because let me put it this way, where C is equal to X minus F T. Right, from here also. So this is basically the implicit solution of the inviscid Burgers, right? Because the inviscid Burgers, the speed, look, here's the F. The speed is played by, right, by the solution, and actually by the initial profile, right? So we recovered, now for a generic data, F, we recovered the inviscid solution given by the method of characteristics. So this is solution, implicit solution. So this is the solution that we also had from the method of characteristics that came out of this very complicated guy when we pulled the epsilon down to 0, right? So we recover the inviscid solution. And that's why this is basically a strong limit, because just you don't have to do anything, right? Take the limit, and it's complicated, but it works, right? For the dispersive case, which is the KdV, then oscillations come in, you have to integrate, but it's much more complicated. It took a while for people to prove it, right? It was basically in the 70s, or I think even later. Peter Lax with David Livermore were people that proved of the dispersive limit going to 0. It's much more, it's a weak limit, complicated, but I think important that people were able to nail down in PDEs. Okay? Okay, good. Right, any questions? Right, so I skipped some points, a little messy, but the main idea is here. So let me also, in a sort of give you maybe our last topic of PDEs and applications, and also mention in a superficial way, but which is good for you to be aware and know things. And I think have just time to finish this up, right? So let me erase the other one because I'm going to need it. So I'm going to do something sketchy, also very preliminary, along the lines of biomath. Right, which is very, very important, very interesting. There's a book which I find it very interesting. I'll give you the reference in a second, by Murray, a very classic book on mathematical modeling in biomath. It's something that I'm not an expert, but there are many interesting problems. So let me mention a few things. So some facts on PDE and applications. In biomath. Very, very superficial. I mentioned already the book, which I like. I like very much this book. I think it's a very nice book. So there's a book by J.D. Murray, which is called It has 2 volumes. It's Mathematical Biology 1, and the first one is an introduction. The date is 2001. Okay, so some of the things I'm going to mention, it's in the notes that are scanned, or were scanned a few pages from this book. So let me start a little bit with, so I can motivate things for you, right, and give you a very brief introduction to at least the equations, right? No, I'm not even talking about any theory, just the equations. So if we look at ODEs in this topic, what comes to your mind? If I talk, maybe you've never seen it, so nothing comes to your mind. Maybe you've seen something, but what comes to your mind if I talk about an ODE, the most simple ODE, in the most simple model, say, in which you're considering some biological system of object. First, not even a system. Then I'll tell you about a system. What do you think of? Population dynamics. Exactly, population dynamics. In the most, say, simple equation, population dynamics, so ODE, there's, say, the logistic growth of a population. So if I have the population N of T is like a density of number of individuals, right? So this is not the most, this is the second most simple equation, at least as I would say. Why is the second most simple equation? Because the simplest equation is this one, right? But it's so big. It's just, so this one, the simplest equation, is basically exponential growth of a population, right? But this one, which is nonlinear, is more interesting, right? It's very simple. So K would be called the carrying capacity, okay? R has to do with our growth parameter, okay? And why is this model, right? This one is just exponential growth. It's a very simple equation. Not very realistic because the population goes on forever. You imagine you're in a scenario where there's food, everything is good, right? In hypothetical scenario. Now comes this nonlinear equation, which is a little more interesting, a little more realistic. And why is K called the carrying capacity? Because when N is equal to K, or let's put it this way, N is equal to K is a stationary point. It's a critical point of the ODE. The ODE has two critical points. N equals to 0, nothing happens, right? So it's a trivial point. And N equals to K, the vector field shuts down. It's 0, it's a critical point. It's sort of an equilibrium point. Is it stable or unstable? To be seen, okay? Now, why is it called a carrying capacity? Because if N is greater than K, this guy is negative and the solution decays. If N is smaller than K, this guy is positive and the solution still grows. This guy is smaller than 1, sort of locally, effectively, the growth rate slows down a little bit, right? So it still grows, but this guy is smaller than 1. So basically, if we do a schematic graph, which is very nice to do with this type of problems, if I put here N and I put here time, this is K. It's a stationary point, right? So is 0. And we can sketch the solution like this. If the solution is here, it sort of grows exponentially, and then it starts tapering down and asymptotes here. Here the same thing, and here it sort of decays like this. Right? So we'll come back to this equation, right? To this logistic equation, and we have basically N1 equal to 0, N2 equal to K are our critical or stationary points. Okay? You can actually write the solution like this, but you can sketch it that way. And you can also linearize about stationary solutions. Remember that when we did the interface problem, we linearized the problem about the stationary solution, which was the shear flow with a flat interface. I mean, these are even simpler. So about N1, we have the equation dN dt, okay, is sort of approximately R of n, and about N2, dN, let me put it like this. Okay, so this is basically the solution about this point, push no, which is one of the stationary points, right? So you can check, you could linearize, so you have these two dynamics and so on. Okay. Let me mention very quickly, because you see how you could do that, which is just to mention something, a system. Now this is for one population. There's another famous one, Lotka-Volterra, sometimes also called the prey-predator model. Okay, so this is, have you ever seen this model? This is also a very well-known model, prey-predator. Sometimes in books, these are considered, say, rabbits and fox and so, right? And this model, you can think of it, right? These are densities, because sometimes the initial population is 3.5 rabbits, right? It's 3.5 rabbits, is right? It's a density by, say, square meters or whatever, right? And what is this model saying? Briefly, right? If one were to deduce it, it has to do a little bit with probabilities of one seeing the other and so on. But look, if I forget the nonlinear terms here, right? If I forget the nonlinear terms here, this model is saying like this: there's enough numbers of carrots or whatever, lettuce, the rabbits do not have a problem with food. And if there's no fox, and they grow exponentially, right? The foxes, on the other hand, they feed on the rabbits to some extent. So if there are no rabbits, N1 is 0, they decay exponentially, the population, right? But then its growth rate of the foxes depends both on rabbits and foxes, because if there are too many foxes, whatever, or right, they reproduce more, but then they could, decline and so on. The same thing. So how do you analyze this system, right? In a sort of a near stationary points, right? You can do similar to what is done. So the critical points of this system N1 star, N2 star, let me call this critical points, is equal to 0, 0, and it's also equal to K4 over K3. Okay, so there's like two critical points. So maybe it's instead of, let's put it like this. is the best way to write, okay? This is a trivial, not interesting, critical point. Is there a population dynamics without rabbits and without foxes? No, right? And these are the critical points for rabbit foxes where basically the population is kind of stable, okay? How do we find these? Well, just check here where the vector field, the right-hand side, is equal to 0, right? Because that makes this thing not very. But now, to understand, so here's a way that I like to present it. It's very simple, right? This you can teach, undergraduate course. Very simple because it connects a little bit with the way we've been doing things, which is this. So to understand, if I write this ansatz, look at that. I'm not doing anything. I'm just writing an ansatz. So if I write this, what am I telling my readers, my audience, with the notation we have used until now? Basically, look, you can say, oh, I see what André is doing. André is basically starting to think of that his population dynamics is going to be near a critical point. And if I plug this into here, and I find an equation for n tilde 1 and 2, I'm going to find an equation for the fluctuations of the populations about that critical point. We did this already a few times in the course, right? So if we do this, and we get the order epsilon equations, which now you know what it is, right? You plug it in. It's not, look, it's not a power series expansion here. Like that more complicated ansatz, it's a simpler thing. This is not a power series expansion. This is just saying I want to see the dynamics near the critical point, right? That's exactly what it said in mathematical language. But then, if I plug this in here, I'm not going to get an infinite series of powers of epsilon because my nonlinearity is quadratic. So if I plug this into here, I basically have something that stops at epsilon squared. So my order epsilon equations are going to basically be just by throwing away the order epsilon squared term. There's no epsilon cubed term here, right? And what happened to the order 1 term? It's 0. Why? Because this is a critical point. It solves, right? It's like, right? See, it's simple. I know. If I were you, I would be hesitating a little bit if I'm seeing it for the first time, but it's 0. It's just like what we did for the interface problem, that we're perturbing about the stationary solution. So the first terms, the order 1 term, if you had done cranking the wheel for the interface problem, you would have seen that it was 0, right? Because it's a stationary solution. It's a solution, and here's this stationary solution. Okay, and look how the system becomes. Okay, this is the order epsilon equations, right? Sorry, I wanted to save space. So if I had asked you, so this is the thing which I think is important. If I had asked somebody like you, linearize these equations here, right? If I say linearize these equations, our first impulsive feeling is just to go like this. Cut this guy out and cut this guy out, right? But that would have been a not very good linearization. You see what I'm saying? Right? If I say linearize this equation, one would like just say, okay, drop the nonlinear terms. But that would have been a bad idea. And that's what I'm about to show you. Why would it have been a bad idea? Because I have two critical points. So look, now what I'm doing here is, this is an educated linearization. Here it's a little bit of a brute force one. Here's an educated linearization because I'm trying to look at the order of epsilon terms near this critical point. I get this super simple system of ODEs. Okay, and now I have two choices for this simple ODE. I can put N1, N2 star either 0 or this guy. Okay, let's put 0. If I put 0, N1, N2, 0, I'm going to get, look, just K1 minus K4, which says that if I'm near a very, very low density population, rabbits grow exponentially and foxes die exponentially. That's a very trivial scenario. We could have guessed that from the beginning. You agree with me? Right? But now, if I had crossed this guy and this guy, that's exactly what I would have seen, K1 and minus K4. But I would have not seen the second possible dynamics about a critical point if I had crossed these guys out. Okay? Now, if I look at this linear system from my systematic linearization rather than the brute force linearization, okay, I see this system. And now look at this. Now the eigenvalues, so how should I write this? Now, for the second critical point, so look at this. If I make the first critical point, my matrix is already diagonal. Okay? But if I make the second critical point, plug in these values here, this is a 4. If I plug in these values, I'm going to have a full matrix because this is non-zero, 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 non-zero. Then to check the stability, I do what? I look at the eigenvalues, right? So for the second critical point, the eigenvalues 1 and 2 are equal to plus or minus I, the square root of K1, K4. Okay, just trust me. I mean, it's trivial, right? I don't want to spend time. So what does this say? This says that I have imaginary eigenvalues, which kind of tells me what? E to the I, something oscillates. Okay? And if we check this, in a phase plane or phase portrait, okay, which is a graph of N1, N2, okay, what will I see? What will I see is that I have a critical point here, the 0, 0. Here's my other critical point, okay, which is the second critical point. And what we will see is that since this is an imaginary eigenvalue, this gives me oscillations. And actually, one can check, that's a little bit of a more hard to test, that actually there's something going a little bit like this, an orbit a little bit like that. Okay, and here an orbit like this, right? To see this big thing here, you would have to solve the problem more completely. But what our linear analysis did is this. What our linear analysis did was a window here and the window there. Do you agree or not? I will say more, but let's see if you agree or not. I see some of the faces a little puzzled, a little like, what does Andrea mean, right? Look, the order epsilon equations, so look how all this perturbation we've been doing. The order epsilon equations for this ansatz means I want this equation tells me how will be the dynamics near the critical point, right? That's what is written mathematically, and I'm reading it in English, right? So let's look at the dynamics near the first critical point, we saw it was a matrix with diagonal matrix with K1 minus K4. Look, K1 sort of growing and K4 decaying in this window. You can't see the rest because this equation is incomplete. It's just an order epsilon equation that is only good for epsilon small. Okay? Now the second one tells me that I have imaginary eigenvalues. So here it is. It's a closed cycle. It's oscillatory, right, if you solve this system. And what does it say? This is a stable point that it says that it's an oscillatory solution which says this. It's a little bit like children on the seesaw, gangorra in Portuguese, seesaw, which is as the population of the rabbits sort of grows, right, then eventually, right, if there's a small population of rabbits, the foxes decay. But then the population of rabbits grows because the fox is not eating the rabbits go. But then there's a lot of food, then the foxes start eating the rabbits start decaying, the foxes start growing, and it stays like that. This is what this window is saying. Agree? Right? Because this imaginary eigenvalue. Okay, so what I wanted to show now, and then I'm going to do the last thing. This is a little bit, I don't even remember if this is in Murray's book, but it's in my notes. What I wanted to say is this, because I'm going to connect with Murray's book and then I'll finish today's class, is that, because the sky is the limit, right? I'm just giving you a little bit of a look into the sky. So this is a very simple model for one population with a carrying capacity, blah, blah, blah. And it gives me this nonlinear OD that behaves like this. This is the one with two populations in the competition, but I wanted to show to you things similar to what we've done before, right? Perturbation analysis, order epsilon equations, eigenvalues, stability, blah, blah. So this is unstable point. This is a stable point because this one, if I just move out, it goes away, right? But then eventually will return back, but nearby. Okay, now, to finish off, basically this very brief presentation, is that then in Murray's book, he presents in chapter, so Murray, chapter 13, section, he has what's called the Fisher, it's a very famous equation, Fisher-Kolmogorov equation, which is like this. So see, it's a PDE. If I didn't have the D is a diffusion coefficient. If I didn't have diffusion, it was that equation we just saw. Right? The logistic. And with the diffusion, so this is called the reaction diffusion equation. Because of this nonlinear term, sometimes it appears also in chemical problems as a reaction term and so on. So, okay. And so K is again our capacity term, D is our diffusion term. And then in the book, so normalize. So now I'm going to go like very fast, like highlights of some of the things in Murray's book, so we finish. Okay, so normalize, or which is dimensionalized, right? Non-dimensionalized, so we get this. Whoops. Okay, and then one can ask for this. So as good mathematicians, you can write this, and your reader knows what you're thinking about. Do you agree? What am I thinking about? What I would like to do, when I write this on the board, what I'm telling you, what am I, or the book, what are we trying to do? Basically, we're asking, there's a kind of a question here, right? I actually tell this story. Every time I tell this story, I tell the story that I heard from my great teacher who had my PhD, which was a great probabilist, Professor Monroe Donsker, that said that he discussed in Japan, there's a very good probability school, and he went to Japan and he discussed math for 1 hour with some famous Japanese mathematician, many famous one is great famous one is Ito, but I don't know if it was Ito, and it was a Japanese professor that didn't speak very good, or some Japanese, maybe, I don't know, mathematician didn't speak very good English, and he didn't speak Japanese, and he would say, he spoke for 1 hour math. He would write this in the book, and he would say, on the blackboard, and then his colleague would say, oh, wow, yeah, and then he would write something else, and they were showing things they were thinking. Right? So if I wrote this on the blackboard, you say, oh, you're looking for a traveling wave solution, right? I don't have to write that. I don't know how, because basically it's saying, is it possible that this equation with a reaction term and the diffusion, we know that for the diffusion, the heat equation, we don't have a traveling wave solution, right? But if we put this, can we have? And there are scenarios where one can have a reaction diffusion equation. Okay, and in the notes, let's see, I got it. Yeah, here it is. I didn't separate. So then you get an equation that becomes like this. You see if you can solve it, and you may and you ask, for example, say if u tends to 1 when z tends to minus infinity, u tends to 0 when z tends to infinity. So you have a wave a little bit that looks like that wave we had, and so on. Can one, what does one get? And then in Murray's book, he rewrites this using u prime as capital V, and then he rewrites this as dv du equals to minus cv minus u 1 minus u over V, and then checks for the phase portrait in the UV plane, and so on. So I don't have much time. I mean to do it super sketchy. Looks at eigenvalues to see stabilities of critical points and so on. So that's a little bit, again, as today's one of the final days, a day full of commercials, right? Full of propaganda. So one propaganda here is of the book of Murray, which is very nice. And then he does that, so he basically transforms, right? One transform, he didn't do this, and it was Fisher and Kolmogorov, right? Gets the Fisher-Kolmogorov equation, asks for traveling wave solutions, and under certain hypotheses, it looks like it's feasible. He writes this ODE, checks critical points and so on. And again, the sky's the limit, and here's a new class, which also I'm not a specialist, but I find it, but it's very fascinating. There's like tricky sometimes to do it numerically, and there's methods numerically specialized for reaction diffusion equations, where this is one thing at least I wanted to mention, reaction diffusion equations that appears in many scenarios, including in fluids. This is population dynamics, right? In fluids you have reaction diffusion when there's a chemical process. Sometimes these problems are very complicated numerically too, because sometimes it is scaled in the way that this term and these terms sometimes are, these terms are in different time scales. Imagine if you're doing it with a chemical, right? A reaction in a chemical is very fast, right? And then other things are slower. So you have a multiple scales in time. But we already talked about multiple scales, multi-scaling in this course. So you see, I mean, the sky's the limit. Many things I don't know, I wish I knew. And this is a little bit where I want to leave things, right? This class today was a little bit impressionistic, like paintings, right? Just a little dot here, a little dot there, a little dot there. But to give you a picture of other things that we didn't look in detail in the course, from asymptotics of integrals, this and that, to other models, biomath, and that is. So next class will be our last presentation, okay? And I'll finish here today. Obrigado.